Hello students, I hope you all are keeping well. I also hope that you are studying consistently, right? Don't lag behind. As your syllabus are going on, you also need to study and learn the taught topics, right? Okay, let's proceed with the next topic. In the earlier section, we have discussed indirect methods for measuring distances. Basically, we have discussed reflection or echo method, right? In this case, we will consider some other indirect methods for measuring distances, right? Let's start with how to find the size of an astronomical object. The size of an astronomical body or an astronomical object. Like we intend to find the size or the diameter of a moon. So there can't be any direct method, isn't it? So we calculate it by some indirect method, as I will illustrate. Suppose this is the Earth's surface and this is the observation point, right? This is the observation point, and this is the moon. This is the moon whose diameter is to be found. Suppose these are the 2 points A and B, diametrically opposite to each other. So AB will be the diameter or size of the moon. Now what to do is, we'll place a telescope over here, high resolving telescope. A telescope is an optical instrument that can be used to measure the angular separation between any two given points, right? So these are the 2 points and it can measure the angular separation. That is, this angle can be easily measured. So I join AO and BO. So this is the linear size and this is the angular size or angular diameter. Let it denote by theta. And suppose this distance is S. S is the distance of the moon from the earth, which we have discussed yesterday. By laser method, the distance of the moon from the earth's surface is found to be about 3,84,000 kilometers, or approximately 3.8, or you can take 3.9 into 10 raised to 8 meters. So this distance is known to us, right? And theta, which is the angular diameter of the earth, it can be easily found by using a telescope. It's an optical instrument which can be used to see the magnified image of a very, very far away object, and it can also be used to determine the angular separation between any two given points, right? So this distance is huge as compared to this distance D. S is very, very large as compared to the diameter or the size of the moon, right? So basically, AB can be considered to be an arc. AB can be considered to be an arc of radius S. So in that case, we are aware of this particular formula. Angle is equal to length of the arc divided by radius, right? So angle over here is theta. Length of the arc over here can be taken as diameter D, right? And radius, it is S. So the diameter of the moon would be given by S multiplied by theta. So theta can be determined by using an astronomical telescope. S, which is the distance of the moon from the earth, which we are aware of, it can be determined by laser method. So knowing the value of S and theta, the diameter of the moon can be easily calculated. And it is found that the size of the moon is about 1/4, that is quarter of the size of the earth, right? And theta, it's found to be 0.5 degree. Through astronomical telescope, it is found to be 0.5 degree. So this is the angular diameter of the moon. So this is one of the method in which the size or the diameter of an astronomical object can be determined, right? Okay, next we'll discuss parallax method. We'll discuss parallax method. In order to understand this, you need to first understand parallax. What actually parallax signify? Now look, I'll give you a simple example. Suppose this is the marker, right? And these are the two observation points. This is the right eye and this is my left eye. And I intend to see this with respect to the background, which is the wall of the room, right? If I close my this eye and look through this eye, and then in the second step, I close my left eye and look the same object through my right eye, then what I find is this position of this object tends to shift with respect to the background. So basically, when an object is seen from two different observation points with respect to the background, then its position tends to shift. There is a relative displacement or relative change in the position of an object when seen from two different observation points with respect to the background. That is known as parallax. Clear? So, there are some technical terms used in the case of parallax. I'll show you. Suppose this is the left eye and this is the right eye. This is the left eye, and let us consider this to be the right eye. Right? This is the right eye. This is the object I am talking about. Now you can join these two lines, and you can join these two observation points, which I have assumed to be left eye and right eye. The distance between these two observation points is known as the basis. It is denoted by a small letter b, right? And the angle subtended by these two lines at the object is known as the parallax angle or angle of parallax. Theta is the parallax angle. Right? So these are the two terms. It is also known as the angle of parallax or parallax angle. So these are the two terms which you need to be aware of. This is the basis, which is the distance between the two observation points, and the angle which it subtends at the object, that is the parallax angle or the angle of parallax. Now look, in case I view a distant astronomical object, then the distance of that astronomical object is very, very, very large as compared to the distance between my left eye and right eye. Or in other words, the distance between these two observation points, which happens to be my right eye and left eye, is negligible as compared to the distance of that astronomical object. So, if this distance is very, very small as compared to this distance, then angle theta would be negligible. So, while measuring astronomical distances, this theta is found to be too small to be measured. Right? So, in that case, we can't take left eye and right eye as the two observation points. Instead, what we take is, we take two different Earth stations at different points on the Earth's surface. I'll give you an example. I'll draw a diagram in order to convince my point. So basically, we'll consider two different observation points, right? Two different observation points on the Earth's surface. So, this is suppose the Earth. This is the astronomical object I am talking about. This is the astronomical object, which is at a very, very far away distance, right? And these are the two observation points. This Earth station E1, this is the Earth station E2. So the distance between these two can be easily found. It is known as the basis, that is represented by B. Now look, the angle is to be found, the angle of parallax is to be found, this will be the angle of parallax. Combine these two, and this will be the angle of parallax. Now if I consider this to be left eye and right eye, then this theta can't be measured. It would be too small to be measured. And hence, we are considering two different observation points, right? Then only theta would have some finite value and it can be measured. Now, how to measure this theta? In order to employ a parallax method, what we do is, we consider any reference star, which is at a very, very far away distance, at a distance greater than this particular object, whose distance is to be found. So, suppose this is the star I am talking about, at a very, very far away distance. So, with respect to this star, this angle phi 1 can be easily determined using a telescope, right? This is phi 1 is the angle which this line subtends with this particular line. So phi 1 can be found by using a telescope. This is a reference star. This is a reference star which is at a very large distance. At a distance farther away from this object whose distance is to be calculated. Suppose distance S is to be calculated. Clear? Now look, when this star is at a very far away distance, then at both the positions this reference star will appear to be in the overhead position. Isn't it? This is very logical. This distance is very small as compared to the distance of the reference star from the Earth's surface. Therefore, at both the observation points, the reference star will appear to be in the overhead position. This is a logical assumption. In astronomy, we need to consider some logical assumptions. So, with respect to the same reference star, we can calculate the angle phi 2 over here. So, this will be it. There is not a different star, it is the same reference star. These are the two same reference stars. It is only because the reference star is taken to be at a very far away distance. Therefore, at both the observation stations, the star will appear to be in the overhead position. So, with this reference star, the angle phi 1 and phi 2 can be easily experimentally determined with the use of telescope, right? So, it can be easily verified if you draw a line over here. Now look, this angle would be equal to this angle and this angle would be equal to this angle. So what I mean to say is that this angle would be phi 1 plus phi 2. That is, angle of parallax would be phi 1 plus phi 2. These two angles are determined at these two Earth stations. They are known, right? So theta angle of parallax is known. Now coming back, we are aware of this formula. Angle is equal to length of the arc divided by radius. This is the formula. Now consider this to be an arc, E1, E2 to be an arc, right? This is the length of the arc, this is the radius, and this is the angle which this arc subtends at the center. So it can be considered to be an arc. Again, this is also an astronomical object. So its distance is also very large, isn't it? So it can be considered to be an arc of radius S subtended in an angle theta, which is phi 1 plus phi 2 at its center. So using this formula, what we get is theta would be equal to length of the arc, that is B, divided by radius, that is S. Or S is equal to B by theta, which is B by phi 1 plus phi 2. So by using this formula, knowing the value of phi 1 and phi 2 and knowing the value of B and substituting its value over here, the distance of this astronomical object from the Earth can be easily determined. So this is all about Parallax method. So this is again an important indirect method to determine the distance of an astronomical object, right? There are some other methods as well, right? That also we will discuss. Next one is using this another indirect methods, Kepler's third law. Now look, in the subsequent section in the unit gravitation, we will discuss laws of planetary motion. We will discuss geocentric theory, we will discuss heliocentric theory, all were discarded, and lastly this Kepler's laws of planetary motion was found to be valid. So there are three laws basically. I will be now restricting myself only in the third law. I am concerned about that only. So by considering third law also, we can easily find out the distance of an astronomical object revolving around the sun by knowing its time period. Time period means the time taken by the astronomical body to complete one revolution around the sun. That will be the time period. So, let's first discuss the statement of Kepler's third law, and thereafter we can easily get the mathematical expression and use it. Okay, now look. Third law states that the square of the time taken by a planet to complete one revolution around the sun, it varies directly as cube of the semi-major axis of its elliptical orbit. Here I need to make you understand regarding the elliptical path and semi-major axis. This is the elliptical path. Actually, all the planets, including Earth, revolve around the Sun in elliptical path, right? And there are two focus. So this is where the Sun is placed. So all the planets, including Earth, revolve around the Sun, with Sun positioned at one of its foci, and all the planets revolve in the elliptical orbit. So this one is known as the major axis. It can be represented by 2a. It is the major axis. While this distance, it is somewhat smaller. This distance is known as the minor axis. It may be denoted by 2b, right? So A stands for semi-major axis, half of the major axis, that is semi-major axis. So A here is the semi-major axis. Because as the planet revolves around the Sun, its distance from the Sun will keep on changing. So we take this value, A, to be the semi-major axis, right? So Kepler's third law, there is a mathematical verification for this, but presently we will be using this statement, right? So Kepler's third law states that the square of the time taken by a planet to complete one revolution around the Sun is directly proportional to the cube of the semi-major axis of its elliptical orbit. So that's the statement. So if we consider two planets, suppose Earth is one of the planet, and we consider the other planet whose time period is known to us, but its distance from the Sun is to be evaluated, right? So for Earth, suppose T1 square is proportional to A1 cube. A1 would be the distance of the Sun from the Earth, which is equal to 1 AU, astronomical unit, which we are aware of. For any planet, for any other planet whose time period is known to us, it can be written as T2 square is proportional to A2 cube. Fine. Dividing these two, we get T1 square divided by T2 square is equal to A1 cube divided by A2 cube. The proportion sign will get eliminated, isn't it? So, A2 cube, it would be equal to T2 square divided by T1 square into A1 cube. Taking cube root, what we get is A2 is equal to T2 by T1, it will be 2 by 3 multiplied by A1. This is the formula I was talking about. Now look, time period of Earth around the Sun, that is known to us. The time period of the planet whose distance from the Sun is to be measured, that should be known to us, right? So knowing the value of T1, T2 and knowing the value of the distance of Earth from the Sun, which is 1 astronomical unit, and substituting the value over here, A2 can be calculated. What is A2? A2 is the distance of that planet under consideration from the Sun. So this is another indirect method which we have discussed so as to find out the distance of a planet from the Sun. So this was another very important and interesting indirect method. There is another method as well, which is known as Copernicus method, right? And there are certain drawbacks in this method. The first drawback is that Copernicus method is valid only when we consider the path of the planet revolving around the Sun to be circular. And the second drawback is that Copernicus method can be used only to find out the distance of inferior planets. Now question arises, what are inferior planets? There are inferior planets, there are superior planets. So inferior planets are those planets whose orbital paths are less than that of the Earth. They are known as inferior planets. Example obviously would be Mercury and Venus, isn't it? Mercury and Venus are the two planets whose orbital path is less than that of the Earth's orbital path. The rest of the planets, they are known as superior planets. So, we will discuss Copernicus method. So as I told you, this method is applicable only to determine the distance of inferior planets. Inferior planets are those planets whose orbital path are less than that of the Earth. And second is, Copernicus method is applicable only when we consider the path of the planet around the sun to be circular. Right? So these are the assumptions we need to consider while discussing Copernicus method. So this is suppose the sun, and this is a perfect circular orbit. Actually all the planets revolve around the sun in elliptical orbit. But Copernicus method is based on this assumption. This is the orbit of an inferior planet, say, and this is suppose the orbit of Earth, which is again, I must say, assumed to be circular. Actually it is elliptical, but here we will assume it to be circular. So this is any planet. Let us denote this by P, Sun by S, and this is Earth. Let us consider this to be Earth, and let us denote it by E. Right? Let this distance be REP, distance of the planet from the Earth. This distance be RPS, and this distance be RES. Now the distance of the Earth from the Sun is known to us. It is 1 astronomical unit. And we are aware, 1 astronomical unit is 1.496 into 10⁻11 meters. Right? Now look, as per assumption, we are considering the paths to be circular. This I must mention time and again. Right? So the distance of the planet from the Sun, or the distance of the Earth from the Sun, these two will remain constant. These two terms will remain constant since we are considering the path to be circular. But this angle will change. And if this angle is 90 degrees, then this angle is found to be maximum. Let us represent it by E. This angle is known as planet's elongation. This angle is known as planet's elongation. Right? So again I am repeating. This method is based only on the assumption that the planets revolve around the Sun in circular orbit. Right? And this method is applicable only to determine the distance of the planet from the Earth or from the Sun, of those planets which are inferior planets, having orbital path less than that of the orbital path of Earth. Right? This is the planet, this is the Earth. The distance of the planet from the Sun and the distance of the Earth from the Sun would be constant. Right? But as the planet and the Earth revolves, the angle E will get changed. This angle of E, which is known as planet's elongation, will be maximum when this angle is 90 degrees. Now what to do is, it's a right angle triangle. We can make use of trigonometric function. So consider cosine, cos E. It will be equal to base over hypotenuse, that is REP divided by RES. If RES is equal to 1 AU and REP is measured in astronomical unit, then REP is equal to cos E. Put this as equation number 1. Right? Second is, we'll consider sin E. Sin E is perpendicular by hypotenuse, that is RPS divided by RES. Again, if this is considered to be 1 AU, which is known to us, it is the distance of the Sun from the Earth, this will be also in AU, astronomical unit. So in such a scenario, RPS, it will be equal to sin E. Now look, if the distance of this planet from the Earth is known to us, it can be determined by laser method, then substituting the value of REP over here, the value of planet's elongation can be determined. And after finding the value of planet's elongation, substitute this value E over here. So the distance of the planet from the Sun can be also determined. Clear? So this was another indirect method. So we have discussed various indirect methods of finding size of an astronomical object or to determine the distance of astronomical objects. Right? I hope you will study all these topics thoroughly. Right? So please concentrate on your studies and do study consistently.